this video is yeah, just going to deal with more on maximum likelihood estimation. The reason we studied, I wanted to include it in this course. This is an applied regression course, but the combination of MLE and for example Bernoulli distributions are very important in logistic regression. That's going to be one of our later topics. And then also we've got we're going to need to examine the our beta coefficients as estimators of a bigger model, as estimators of parameter coefficients. So we're going to get into maximum likelihood estimation throughout the study of regression. Well, not throughout, but it's going to pop up enough to where I felt like it was worth our time to spend at least 3, possibly even 4 videos on this. So, guys, the last time, I think this is video number 14. No, I think it's not. I think it's video number 15. So, in video number 14, we looked at a couple of really simple, trivial examples. If I remember correctly, we looked at the percentage of the proportion of times that a coin was flipped, and we got a tail, and no, we got a head, okay, and we kind of ended up thinking that the best estimation of the parameter of the distribution would be equal to this value. We also looked at a sample mean. I think our sample mean was 105, and we had 3 pieces of data. And we kind of come up with that most likely the estimate of the unknown population parameter mu would be the sum of our data over n, which we all know is clearly the sample mean. Well, all that seemed intuitively clear, and it turns out everything we did was correct, and it turns out that these things are correct. But there's a lot more to learn about MLEs than just what we looked at. Plus, it turns out that obviously not all problems are this simple, and of course, as the number of parameters increase, the problems get more difficult, and so we're getting ready to go in a little bit different direction. Now, let's kind of set the framework for what we're going to be doing here. So we're going to be given some data, and I'm going to use, there we go again. So we're going to be given some data. Y1, Y2, Y sub n. And I want to look at our situations where we have the continuous case. So we're going to have f of y sub I given some parameter. And let's see, we'll say that this is our density function, and we will look at the discrete case. And in this situation, we'll look at the p of y sub I given some theta. And obviously, we'll refer to this as our mass function. Now, we're going to assume that, in the continuous case that we have independence. And we're also going assume that we have what's called IID. This is called independent and identically distributed. And of course, these two are clearly combined. Identically distributed just means that every observation comes from the same distribution with the same parameters. So we're not like flipping a three-headed coin and a two-headed coin in the same, and creating data from those two different things. So so guys, right here, let's set up a goal. And our goal is to find a value of still haven't gotten used to writing with this pen, but it is getting better. That maximizes the likelihood function. So guys, when we do that, we're in good shape. Now, we looked at two really simple examples. So let's look at this. Likelihood function. Well, really happy with the way this is going. All right, let's look at the likelihood function. And let's first of all look at it in terms of the discrete case. So we would say that in the discrete case that we have the likelihood function of theta given our data. And in the continuous case, we have the likelihood of our data given a parameter. Now, in both situations, our likelihood, and actually what I'm going to do here is just look at the continuous case. So the likelihood of our y sub i's given theta will be found, because these things are independent, of got it. I don't know why, but I'm really struggling with writing this today. Okay. There's a certain place on this pen that doesn't hang up as much. Anyway, because we have independence, we could set up the product. And we're going to call this the likelihood function of theta, which is our parameter. So the idea here, the major idea, is we have an independent random sample. And the likelihood function, theta, given our data, is going to be equal to the product from I equal 1 to n ability. And that should be y sub I. All right. Now, got a couple things working for us here. If I don't really know how I want to say this. Well, we can show that the if we take the natural log, guys, again, I'll give extra credit if somebody can figure out how to do that to get that back. But so if we have an increasing function, okay, the beauty of this. Boys and girls, I got a lot to learn about this this program. So okay, so we've got this notation. I want to shut this down. I want to start a new one. Again, that's kind of the beauty of having you guys having this on video. The beauty is you get everything and you can pause it and stop it and go back and so on and so forth. The bad thing is I can't cover up my mistakes. So we have an increasing function. Yes, please accept my apologies for this, but there's certain places I can find on this pen where it writes perfectly, and there are certain places that I can't. So, guys, at the end of the day, if we take the natural log the maximum value of the natural log of our likelihood function is the maximum of our likelihood function. And you're going to see that we're going to take the natural log of things because in many cases it makes the calculations of our derivatives easier. Now, speaking of derivatives, we learned back in Calc 1 that if we have some function that maybe looks like this, in this case we clearly have a global max at this particular point, that we can get a lot of information about the value and the value at which it's attained, the maximum, by first of all taking the first derivative, setting it equal to 0. We can look at the second derivative, and if the second derivative is negative, that means that we have a maximum value at this point. Evaluating this point right here, we could look at the first derivative, set it equal to 0, and we could see if the second derivative was positive, then we would have either a local min or a global min. Well, we're going to use that idea here, but before we go on and get too crazy, let's review a little bit about natural logs. Probably something you already know because you guys are math teachers, but I learned years ago assume nothing. So guys, if we take the natural log of a product, remember this is equivalent to taking the sum of the natural logs. If we take the natural log of x to a power, this is the same as y times the natural log of x. Yeah, I hope we don't need this, but you never know. Guys, remember sum from I equal 1 to n. Y sub I is just y1 plus y2 plus yn. And the product from I equal 1 to n of y sub i's is just y1 times y2 times yn. Again, let's take nothing for granted here. Now, let's say that we want to take a look at, I don't know, the error rate of a machine. In other words, we've got a machine that creates a particular product, let's just say a golf ball. I'm sure there's some sort of standards that golf balls have to maintain. And we want to analyze this. So let's, first of all, just assume for technical reasons their error rate is constant. Goes back to the whole IID that we talked about earlier. Obviously, we have an unknown error rate. And our goal use sample data to estimate the error rate. All right, it's going to be fun. So let's just assume that that we record an error at, no, I don't know, let's just say 1, and not an error equal to 0. So guys, let's collect our data, and we see that the first product has an error, second one doesn't, next one doesn't, and so on. And we collect our data. And let's say that we did this, what do you think, 500 times? I'll tell you what, let's bump it up a little bit. Make the mental math easier too. Let's say we did this 1,000 times. So we need our probability mass function. And we will let theta be our unknown error rate. So guys, we've got some distribution here, whatever it may be, and trust me, it doesn't look like that, where the maximum likelihood estimate of our distribution. Let me get rid of that. That was just goofy. Um, we have some distribution, which we have a maximum likelihood estimate at a particular point. All right, let's make it happen. Well, it turns out that you probably know that this is a special case of the binomial distribution, and we can model this using the Bernoulli distribution. Guys, the Bernoulli distribution is just a special case of the binomial distribution. So this is special case. Where n is equal to 1. And it turns out that the Bernoulli distribution can be looked at as this. All right. So when we have in observation 0, which was not an error, we have clearly one minus theta. And when we observe an error, for the y sub i's that are equal to 1, given our parameter, we have just theta. So let's go on to the next screen. So our likelihood function, theta, given our data, is going to be the product of each observation. So we can take theta for our first observation, 1 minus theta to the 1 minus y1 for our first observation. Our second observation, and we'll run this all the way out to our last observation. All right. Now, guys, we'll clean this up a little bit, and you can see that by multiplying all these, that if we look at our thetas, When we multiply with a common base, we add our exponents, so we can look at theta from the sum of I equal 1 to n of y sub i's times 1 minus theta times the sum, I'm sorry, not times sum, to the exponent sum from I equal 1 to n of 1 minus y sub i's. That doesn't look right. Let's see, we got our powers, 1, 1, 1. Yeah, okay, yeah, that's right. Okay, now, let's clean it up a little bit. So this is 1 to n, 1 minus theta, write it real big because it's important. And so, guys, note here, if we have the sum from I equal 1 to n, I don't really know if this is going to make a difference or not, but that ultimately what we have is we have 1 plus y1, 1 plus y2, plus 1 plus yn. So we can rewrite this as, see, so we have 1 plus 1, so we have n of these, minus the sum from I equal 1 to n of y sub i's. Okay, that just doesn't seem, yeah, okay, that's what I want. Now, so what we end up with is theta of some of our y sub i's, because I'm going to drop off the I equal 1 to n because I think we're okay with that. Okay, 1 minus theta n minus the sum of the y sub i's. Now what I want to do, we talked about taking the natural log, and guys, this is clearly our likelihood function. So now I want to take the natural log of L. So I'm going to take the natural log of theta to power sum of yi's. 1 minus theta n minus sum of yi's is the power. So I'm going to take the natural log of this. Now, we saw earlier that the natural log of a power, the natural log of a product is the sum of the natural, well, I'm actually writing pretty good there, well, decent. So we're going to use this. So the next thing we're going to get is we're going to get the natural log of theta sum of our y sub i's plus the natural log (1 minus theta) times n minus sum of the y sub i's. Now, the next thing we're going to invoke is this whole natural log of x to the y power is equal y times the natural log of x. Okay, so we're going to get the sum from I equal 1 to n. I'll start writing these again because it's now easier to write, times the natural log of theta. And now we're going to have quantity n minus the sum from I equal 1 to n, y sub i's, times the natural log of 1 minus theta. Guys, believe it or not, we're making progress. So we end up with and all I'm doing is rewriting the previous page because I want it on this page because we're getting ready to do some stuff. Doug, pay attention. Okay. Now what we want to do is we want to take the derivative. So we'll take the derivative of L with respect to theta. So this is going to be, so the sum of the y sub i's. Remember that the derivative of the natural log is just natural log of theta is 1 over theta. So we're going to have 1 over theta times the sum from I equal 1 to n over y sub i's. And similarly speaking here, the natural log of 1 minus theta will be 1 over 1 minus theta times this mess up here. Now, isn't a chain rule here, so with respect to theta, we'd have to take the derivative of the inside part. So I'm going to play trickery here on you guys. And so this, again, the derivative of 1 minus theta with respect to theta is negative 1. So I'm going to change that for obvious reasons, okay? Well, now what we need to do is we need to set this equal to 0. So we're going to have 1 over theta. Sum from I equal 1 to n, y sub i's. I'll tell you what, I want to rewrite this. I think this, I see what's going to happen in the near future. So let's clean this up a little bit. Okay, so let's write this as the sum of the y sub i's over theta minus n minus the sum of the y sub i's over 1 minus theta. Hope everybody's okay with that. You should be. All right, guys, next step, gonna do the obvious. I'm gonna cheat, so please forgive me. Now, if you need to know why the previous step becomes this step, then you and I need to talk. Okay, so obviously this is equivalent to what we had before. Okay, so let's do a little cross multiplication. So we're going to get sum of the y sub i's minus theta times the sum of the y sub i's equals n times theta minus theta sum y sub i's. Well, we got something really cool here, right? We can get rid of those. So we have that the sum of our y sub i's is equal to n times theta. Guys, we're most interested in theta. So the maximum likelihood estimation of theta in this case would be the sum of our y sub i's divided by n. So guys, what we would do here is we would go back to our original data. Whatever it may be. I'm making this stuff up, okay? And remember, we had 1,000 of those. We let our y sub i's be, no, I'm sorry, let me back up a little bit here. So our best estimate of theta will be the sum of the y sub i's divided by n, which would be precisely equal to the proportion of ones that we have in our data set, in the measurements that that we've collected. Now, are we done? Sorta, but we still need to verify. You know, just because the derivative is equal to 0, we still need to consider whether or not we have a min or a max. So what we do here is evaluate the second derivative. And as we talked about before, look at the sign of the second derivative. And in this case, we're going to see that, I'll probably leave this for an exercise, but in this case, we're going to clearly see that the what we have is a maximum value. So, cool. So, guys, let's summarize here. So, you're going to be doing some of these. So the steps to a maximum likelihood estimation. So first thing we're going to do is we've either going to have the density or the mass function. The previous problem was a Bernoulli, so we had the mass function. Guys, the density function is when we have a continuous distribution. I'm sure Dr. Whitaker and Dr. Lee have taught you guys very, very, very well here. I always say they've forgotten more about probability than I'll ever know. Probably forgot more last night in their sleep than I'll ever know. Second thing, you know, we need a random sample. Funny what kind of crazy data you would get if you're trying to estimate the population IQ of individuals, and you happen to venture into a Mensa meeting and take your sample from a Mensa meeting folks. You get dumb stuff. So we need independence and identically distributed, as we talked about later. So third thing we do, create our likelihood function. So this is either going to look like the likelihood is going to be the product of our f of y sub i's given theta, or likelihood is going to be the product of p y sub i's given theta. And again, depending on whether we have the continuous or the discrete case. The fourth step, how have I got here? Okay, the fourth step. Take the log. Yeah, that's what I mean when I say take the log. Take the natural log. You're ultimately going to take the derivative of the natural log with respect to theta. Set it equal to 0. And obviously you're going to solve for theta. And theta is our estimator. We always should, the sixth thing, you know, this is the part that I so often forget. So verify we have a min or a max, and obviously we're going to take care of this with the second derivative. Now, not sure how I'm doing on time here. Let me check my... 42 minutes. Yeah, I'm trying to set our... I'll tell you what. Hold on just a second.